Hi, I'm Ila Victoria, and together with my group mates, Christoph and Barry, we will be reporting to you about electrical circuits. Now, an equation which involves differential coefficient is called a differential equation. A differential equation involving derivatives with respect to a single independent variable is called an ordinary differential equation, and involving partial derivatives with respect to more than one independent variable is called a partial differential equation. Now, the interconnection of a simple electric device in which there is at least one closed path for current to flow is called an electric circuit. The circuit is a switch from one condition to another by change in the applied source or a change in the circuit elements. There is a transition period during which the branch current and voltage changes from their former values to new ones. This period is called a transient. After the transient has passed the circuit, it is said to be a steady state. The linear differential equation that describes the circuit will have two parts to its solution. The complementary function corresponds to the transient, and the particular solution corresponds to the steady state. The VI relation for an inductor or a capacitor is a differential. A circuit containing an inductance L or a capacitor C and a resistor R with current and voltage variable given by differential equation of the same form. It is a linear first-order differential equation with constant coefficient when the value of R, L, and C are constant. L and C are storage elements. The circuit has two storage elements like 1L and 1C are referred to as second-order circuit. Therefore, the series of or parallel combination of R and L or R and C are first-order circuit, and RLC is in series or parallel are second-order circuit. The circuit changes are assumed to occur at time t is equal to 0 and represented by a switch. The switch may be supposed to close and open at t is equal to 0. The order of differential equation represents derivatives involved and is equal to the number of energy storing elements. Differential equation is considered as ordinary. The differential equation that form for transient analysis will be linear ordinary differential equation with constant coefficient. Now, the value of voltage and current during the transient period are known as the transient response. The CF of differential equation represents the transient response. Next, the value of voltage and current after the transient has died out are known as the steady response. The PI of differential equation represents the steady state response. The complete or total response of network is the sum of the transient response and steady state response, which is represented by the general solution of the differential equation. Now, the value of voltage and current that result from initial conditions when input functions is 0 are called zero input response. The value of voltage and current for the input function which is applied when all initial conditions are zero are called zero state response. Now let's look at the table. This table shows the elements symbols and units of the measurements. First element will be charge. Charge has a symbol of Q and a unit of coulomb. Next, the element current has a symbol of I and a unit of ampere. Next, the element resistant has a symbol of R and has a unit of ohm. Next is the inductance, which has a symbol of L and a unit of Henry. Next is the capacitance, which has a symbol of C and a unit of farad. And lastly, we have the element of voltage, which has a symbol of V and a unit of volt. Now let us discuss the first-order homogeneous differential equation. This will give us an equation of dy times t all over dt plus py times t is equal to 0. This will give us dy times t all over yt is equal to negative p dt. Integrating ln y quantity t is equal to negative pt plus ln k. Therefore, y quantity t is equal to k times e to the power of negative pt. Next, we will talk about the first order non-homogeneous differential equation. The equation will be dy times t all over dt plus py times t is equal to q. The equation is not altered by multiplying e to the power of pt. E to the power of pt times dy quantity t all over dt plus e to the power of t times py quantity t is equal to e raised to pt times q. This will give us d times e to the power of t y times t all over dt is equal to the integral of q times e to the power of pt times dt plus k. Now this will give us y quantity t times e to the power of pt is equal to the integral of q times e to the power of pt times dt plus k. Lastly, this will result to y times t is equal to e to the power of negative pt times to the integral of q times e to the power of pt times dt is equal to ke to the power of negative pt. The first term above the first term above is known as a particular integral and the second is known as the complementary function. The particular integral does not contain any arbitrary constant and CF does not depend on the forcing function q. If q is constant, then y quantity t is equal to e to the power of negative pt times q times e to the power of pt all over p plus k times e to the power of negative pt. Therefore, y quantity t is equal to q over p plus k times e to the power of negative pt. Now, the formation of differential equation for an electric circuit depends upon the following laws. First law, I is equal to dq over dt. Second law, the voltage drop across resistance R is equal to R times I. Third law, voltage drop across inductance L is equal to L times di over dt. Fourth law, the voltage drop across capacitance C is equal to Q over C. In Kirchhoff's law, the algebraic sum of the voltage drop around any closed circuit is equal to resultant EMF in the circuit. Using the current law, at a junction, current coming is equal to current going. In an LR series circuit, R times I plus L times di over dt is equal to E. This will give us di over dt plus I times R over L is equal to E over L. Now next is the CR series circuit. Ri plus Q over C is equal to E. Now, this will give us R times dq over dt plus qc is equal plus q over c is equal to E. The LR circuit analysis. In this diagram, the switch S is closed at time t is equal to 0. We must find the current through the voltage across the resistor and the inductor. Here, the voltage across resistance is equal to Ri times T. Voltage drop across inductance is equal to L times di quantity T all over dt. From Kirchhoff's law, L times di quantity T all over dt plus Ri times T is equal to V. And it will give us di times T over dt plus R over L times I times T is equal to V over L, which is the first order linear differential equation. Now, IF is equal to e to the power of the integral of R over L dt is equal to e to the power of R over L times T. Now, the general solution of it is e times R over L times T. Now the general solution is e to the power of R over L times T is equal to the integral of V over L times e to the power of R over L times T times dt plus k. It is equal to V over L times e to the power of quantity R over L times T all over R over L plus k, and it will equal to V over R times e to the power of R over L times T plus k. Therefore, I quantity T is equal to V over R plus K times e to the power of negative R over L quantity T. Since the inductor behaves as an open circuit, I quantity O positive is equal to 0. From the first equation, which is I times T equals V over R plus K times e to the power of negative R over L times T, we can therefore conclude that 0 is equal to V over R plus K. Now K is equal to negative V over R. Therefore, I quantity T is equal to V over R minus V over R times E to the power of negative R over L times T is equal to V over R times quantity 1 minus e to the power of negative R over L times T. The voltage across the resistor and the inductor are given as V subscript R times T is equal to I times T times R. Therefore, I times T is equal to V times quantity 1 over e to the power of negative R over L times T. Now, V subscript L times T is equal to L times di quantity T over dt is equal to L times V over R times quantity 0 minus quantity negative R over L times e to the power of negative R over L times T. Therefore, VL times T is equal to V quantity e to the power of negative R over L times T. At T is equal to 0 and I quantity T is 0, therefore VL times T is equal to V and VR quantity T is equal to 0. At T is equal to L over R is equal to pi. Now, I quantity T is equal to V over R times quantity 1 minus e to the power of negative 1 is equal to 0.632 VR. And therefore, VL quantity T is equal to VE to the power of negative 1, which is equal to 0.368 V. VR quantity T is equal to 0.632 V. L over R equals pi is known as the time constant of the circuit and is defined as the interval after which a current or voltage changes 63.2% of its total change.
Okay, good day. Now let's talk about CR circuit analysis. So here we can see the problem. A condenser of capacity C farads with V naught is discharged through a resistance R ohms. Show that if Q coulomb is the charge on the condenser, I ampere the current, and V the voltage at time t, Q is equal to CV, V is equal to Ri, and I is equal to dQ dt. Then V is equal to V naught E raised to the power of 1 over RC. So here we can see the diagram where the voltage across the resistance is equal to Ri. The voltage drop across the capacitance is equal to Q over C. From Kirchhoff's law, L di dt over dt plus Ri t is equal to V, which leads to di of t dt plus R over L times I t is equal to V over L. When after release of the key of the condenser gets discharged, and at that time voltage across the battery gets 0, so V naught is equal to 0, or the initial initial voltage is 0. The differential equation of above circuit is Ri plus Qc is equal to 0, which gives us R times dQ over dt plus Q over C is equal to 0. dQ over dt is equal to Q over RC, which is, when we further simplify, becomes dQ over Q is equal to negative 1 over RC dt. So we integrate this, we get log Q is equal to negative 1 over RCT plus A. So this will be our first equation. So at T is equal to 0, the charge at the condenser is Q naught. Therefore, log Q naught is equal to A. So from equation 1, log Q is equal to negative 1 over RCT plus log Q naught. When we substitute the Q naught is equal to A, we get Q over Q naught is equal to E raised to negative 1 over RCT. So further simplification leads to Q is equal to Q naught E to the power of negative 1 over RCT. And then we divide both sides by C. So Q over C, which is equivalent to V, or voltage, is equal to Q naught over C times E raised to negative 1 over RCT. And then since Q over C is equal to voltage, we get this equation. V is equal to V naught E raised to negative 1 over RCT. So in conclusion, by using first-order ordinary differential equation in LR and CR circuits, we can find the current I and voltage V in the circuit where inductance L or capacitance C and resistance R are given. Okay, let's look at another example from Barry.
In a series RC circuit, the resistance is 5 ohms, the capacitance is 0.01 farad, and the voltage source is 100t volts. If initially, the current is 0, find the charge at any time t. So we have the given of resistance is equals to 5 ohms, capacitance is equals to 0.01 farad, and a voltage source of 100t volts. And the initial values of time is equals to 0 and current is equals to 0. So in solving electrical RC circuit, we will use the formula of resistance times change in current with respect to time plus current over capacitance is equals to voltage source, or R dQ over dt plus Q over C is equals to E. Substituting the values for that equation from our given, we will get 5 dQ over dt plus Q over 0.01 is equals to 100t. Getting rid of the resistance on the left side, we will multiply both sides by 1 over 5. So multiplying both sides by 1 over 5, we will get dq over dt plus q over 5 times 0.01 is equals to 100t over 5. So simplifying that equation, we will get dq over dt plus 20q is equals to 20t. So as you can see, this differential equation is now a linear differential equation. So we will use our knowledge in solving linear differential equation. So this differential equation is linear in Q. So our formula is U times E raised to the integral of t of t dt is equals to the integral of q of t times e raised to the integral of p of t dt dt. So our values for p of t and q of t are p of t is equals to 20 and q of t is equals to 20t. So substituting the values for that equation, we will get now the q times e raised to the integral of 20 dt is equals to the integral of 20t times e raised to 20 dt dt. So solving our integrating factor of e raised to the integral of 20 dt and simplifying the equation, we will get q times e raised to 20t is equals to 20 times the integral of e raised to 20t t dt. So this integral is we will solve this integral using the integration by parts. So formula is the integral of u dv is equals to uv minus the integral of v du. So we will choose our u and dv. In quick tip, we will use we will choose our u and dv based on the liat. So u will get the priority first. So in this integral, we have algebraic and exponential. So our u will be the algebraic, which is the t. So u is equals to t and du is equals to dt. So our dv will be the leftover of the integral. So e raised to 20t dt, which is according to the rule of integral of e raised to at dt is equals to 1 over a times e at. So using that rule, we will get the value for our v, which is equals to e raised to 20t over 20. So substituting the values of u, du, dv, and v in our formula of integration by parts, we will get the equation 20 times the integral of e 20t t dt is equals to 20 times t over t times e raised to 20t over 20 minus the integral of e raised to 20t over 20 dt. So simplifying that equation, we will get I will skip the left side of the equation to make this simpler. So 20t, so we will get 20t is equals to e raised to 20t over 20 minus 20 times the integral of e raised to 20t over 20 dt. So multiplying the constants or bringing the constants out of the integral, we will get 20 over 20t is equals 20 over 20t times e raised to 20t minus 20 over 20 times the integral of e raised to 20 over t dt. So simplifying that equation, we will get t times e raised to 20t minus the integral of e 20t dt. So simplifying, integrating the integral on the right side, we will get t times e raised to 20t minus e raised to 20t over 20 plus c. So we have solved the we now have solved the right side of the linear differential equation. So substituting the value of it in the original equation, we will get t times e 20 q times e raised to 20t is equals to t times e raised to 20t minus e raised to 20t over 20 plus c. So, um, multiplying both sides by 1 over e 20t, multiplying both sides by 1 over e raised to 20t, we will get q is equals to e minus 1 over 20 plus c over e raised to 20t. So bringing the e20t of in the c, we'll get q is equals to t minus 1 over 20 plus c times e raised to the negative 20t. So finding the value for c, we will use the initial value given. So our formula here, q is equals to t minus 1 over 20, t minus 1 over 20 plus c times e raised to negative 20t, and at t is equals to 0 and at I is equals to 0, we will get 0 is equals to 0 minus 1 over 20 plus c times e raised to negative 20 times 0. So as we know, e raised to 0 is equals to 1. So we will get 0 is equals to 1 over 20 plus c. So transposing the value of 1 over 20 to the left side, we will get c is equals to negative 1 over 20. So the value of our c is negative 1 over 20. So substituting the value for the c in the original equation, the solved original equation, we will get q is equals to t minus 1 over 20 plus negative 1 over 20 times e raised to negative 20t. So, simplifying this equation, we will get q is equals to t minus 1 over 20 minus 1 over 20 times e raised to negative 20t. So, that is the formula. That is the formula for current at any time t.